Welcome to our discussion on derivatives and rates of change. As we've discussed before, we know that the problem of trying to find the tangent line to a curve and the problem of trying to find the velocity of an object both involve finding the same type of limit. And this special type of limit that we've been dealing with, we're now going to call a derivative. And we'll see that it can be interpreted as a rate of change in many sciences and engineering. So if we have a curve C that has some equation y equals fx, right, just a standard old function curve, doesn't matter what it is, and we want to find the tangent line to that curve at some point, you can call it point A, and then of course the y coordinate would be f of A. Then we consider a point really close to it. We call that point Q, and just let it be an arbitrary x and f of x, and obviously we have to let x not be equal to A. And we can compute the slope of the secant line very easily by doing change in y over change in x. We do f of x minus f of a equals x minus a. So on this picture we can see very clearly that if we're trying to figure out what is happening here at point A, right, we want to know the slope of the tangent line at that point. Then we pick some other point over here, we call it Q, and we can calculate the slope of this blue line, the secant line, by doing change in y over change in x, right? This is just our differences in our y values, f of x minus f of a, and this is the difference in our x values by taking x minus a, and slope, change in y over change in x. Very simple. And basically what happens is we realize that the slope of this line PQ, right, this blue line, the slope PQ, approaches the slope of the tangent line as we move Q closer and closer to P. Here's an illustration to remind us. So here's the point P on the function. This red line is the tangent line. You can see the slope of the tangent line up here is a little bit bigger than 2. Here's our secant line in green. We have this point here. You can think of this as, right, x, and this is a, and this distance is x minus a, right? And as we bring x, right, we're moving x to the right, which is causing the line to follow the curve, right? It's causing the point to follow the curve. So x is now getting closer and closer to A, and we see what's happening to the slope of the secant line is it's starting to approach that 2. And it's getting closer and closer and closer until they line up almost perfectly, right? And then it'll go undefined and it'll get a little bit too big on the other side, and you can see how when it gets right there, they're pretty much the same slope, and if we actually let that difference go to 0, they will equal each other perfectly. Okay, so that's what we're talking about when we take a secant line and let it approach and become a tangent line. So we can now define the tangent line to the curve at some point A as the line that goes through that point P and has the slope that we've now defined as change in y over change in x with f of x minus f of a all over x minus a, and then taking the limit as x goes to a. Here's an example. We want to find an equation of the tangent line to the parabola y equals x squared, so that's our standard old parabola, at the point 1, 1. So in this example, a is 1, and our f of x is x squared, so we can very easily compute the slope by doing f of x minus f of a all over x minus a. So we have f of x minus f of 1 all over x minus 1. We're going to take the limit as x approaches a, or in this case, x approaches 1. You plug in those values, you figure out f of 1, which is 1, right? Now you've got x squared minus 1 over x minus 1. You try and take the limit as x approaches 1, and you get 0 over 0. And we remember, oh, that's right, when I have 0 over 0, I have to be able to reduce things, right? If they both equal 0, that means they have to have the same factor in them. So they both have to have an x minus 1 in them. You factor out the top. Lo and behold, you find that factor of x minus 1. You're able to then cancel out your problem, right? Cancel out your discontinuity by canceling top and bottom. Now you're just taking the limit as x approaches 1 of x plus 1, which you then go back and reevaluate it by just plugging in the number and see what happens. Then you get 1 plus 1, which equals 2, and yay, you've got the slope of the tangent line is 2. Now that you have the slope, you were already given the point 1, 1, and it's a simple matter of plugging everything into our good old point slope form of a line. Y minus y1 equals m times x minus x1. You plug in the m, you plug in the y1 and the x1, and then you just move things around until it's in the more commonly used y equals mx plus b form, and there is the equation of our tangent line. We sometimes refer to the slope of a tangent line to a curve at a point as the slope of the curve at that particular point. Because if you were to zoom in on a function, you will see that a curve will look straighter and straighter and straighter as you zoom in. And so that tangent line and the curve end up melding together, and you get that the tangent line slope is the same thing as the slope of the function at that point. So basically, knowing the slope of the tangent line is giving us the slope of the function at that particular point. And remember, slope is a rate of change, so the slope of the tangent line is telling us how fast the function is changing at that particular point. And that's really important, because we want to know how fast various things are changing at certain points. Think about a cost function. You want to know how fast your cost is increasing or decreasing, or a profit function, or even something that models a distance or a position. You want to know how fast maybe something is moving in space. All of these things can be modeled by knowing how fast the function is changing. So we've already seen that the standard equation, which I have here on the right, is one way of calculating the limit, right? We have this point A and this other point X, and we're looking at the difference between them. Well, what if instead we just relabel some things? We let X minus A equal H. Then by substitution, X, well, not by substitution, really by simple algebra, X just equals A plus H. And now instead of f of X, you have f of A plus H minus f of A, and then instead of x minus a, right, you have h. So this is just a simple substitution in between these two, right? So remember, originally this point here was just a and f of a, and we let this be x originally, right? And so this was x and f of x. And so this distance here was the difference between f of x and f of a, right? It was just simply f of x minus f of a. And then this distance here was x minus a. Well, now we've just relabeled them. Instead of, kind of thinking of these as two distinct values, it's an a and it's an x, we're relating the two. We're saying, well, if this is a, this is just a plus h. It's a plus a little bit more, right? X was just a little bit to the right of a, so now we can think of x in terms of a and just say it's a plus a little bit more. And it doesn't, always have to be to the right. It works to the left too, but it just works to the right better in our minds. It makes more sense with the a plus h. We could easily do this with a minus h, and everything would be the exact same. So we'll notice that as x approaches a, right, in our original one, as x approached a, as we let x get closer and closer to a, right, in our original thing, as x went this direction and got closer to a, what's happening is this distance is getting smaller, i.e. h is going to 0. And so now with our new limit, instead of x going to a, we have h going to 0. And you might be thinking, why do we bother with all this? Well, because this gives us a more generic definition of the slope of the tangent line. Because now we'll be able to take this and change it to the definition of the slope of the tangent line everywhere instead of just at one particular point A. But that's not what we're going to do yet. Right now we're still going to look at particular points. So in general, velocities are looked at as a rate of change, right? So if you have a function that describes the motion of something, some object, and we call that its position function, then in the interval from t equals a to t equals a plus h, right? So we've gone from 5 seconds to maybe 5.3 seconds, and then h is just 0.3. Then the change in position is going to be how far it had gone in 5.3 seconds minus how far it had gone in 5 seconds. Right, so there's its change in position over change in time, and there's your velocity, right? Velocity equals how far you move in what amount of time. Which tells us now that velocity is another example of this slope, right? A rate of change. Your average velocity is just your displacement over time. It's how much distance you've traveled over how much time has elapsed. And so we can see that average velocity is going to be this simple secant line slope that we've been doing. And as we let that h distance go to 0, and we now have a slope of a tangent line, instead of average velocity, we now have instantaneous velocity. So we can define instantaneous velocity as this exact same thing. It's the slope of the tangent line, and it also happens to be instantaneous velocity. Also very important. Let's look at an example for this. Let's suppose that a ball is dropped from the upper observation deck of the CN Tower, which is 450 meters above the ground. What is the velocity of the ball after 5 seconds, i.e. how fast is it going at that point, and then how fast is the ball traveling when it hits the ground? Now, why would that be something we would want to know? Because for those of you that have taken physics, you know that force equals mass times acceleration. If we know how fast the ball is traveling, we can figure out what its acceleration was, and then we can know what force it's going to hit the ground. So it's kind of important to know these things. We can use the equation of motion, simple equation of motion, as 4.9 t squared, and then by doing our simple limit, we can figure out velocity. Okay, so this original equation, 4.9 t squared, is just the position function. It's the equation of motion. Now we're going to figure out velocity. You plug in a plus h, so you have to do a plus h squared, right, times 4.9, and then f of a, so that's just 4.9 times a squared. You FOIL out your a plus h squared, and that's where you get this piece, right? A plus h squared gives you these three things. And then because you have 4.9 times both things, you can factor that out and then bring the a squared inside. The two a squareds cancel each other. You're left with the 4.9 times the 2ah plus h squared all over h. You'll notice now that everything has h's in it, which is nice, because then you can do the division and get rid of the h, because when you let h go to 0, in these previous ones, you end up getting 0 over 0, which is no good, so you know something has to factor out, which is why we're doing all of this stuff, right? And every time you kind of reduce, it's still 0 over 0, it's still 0 over 0, and then finally at this point, we no longer have that 0 on the bottom. We can let h equal 0, and then we end up just getting 4.9 times 2a, or 9.8a. And that gives us the velocity formula at a point A. Now we can plug in 5 and get 9.8 times 5, or 49 meters per second. Now we can tell you how fast this thing is traveling at any time. If we want to know at 3 seconds, we plug in 3 and we get 9.8 times 3. After 10 seconds, we would get 98, but after 10 seconds, it's probably already hit the ground. All right, now since the observation deck was 450 meters above the ground, if we want to figure out how fast it's going when it hits the ground, we have to figure out how long it takes until it hits the ground. You know, at what time did it hit the ground? So you take that position function and you set it equal to 450. So you take 4.9 t squared, set it equal to 450, and solve. Divide both sides by 4.9, take the square root of both sides, and you get roughly 9.6 seconds is when it hits the ground. Now, to figure out the velocity of the ball as it hits the ground, all we got to do is take that time of 9.6 seconds and plug it back into our velocity function, right, which we found earlier to be 9.8 times a, but isn't 9.8a is the same thing as 9.8t, right? It works for any time. You plug in 9.6, or in this case you could actually go with the more accurate number of the square root of 450 over 4.9, and then you get an answer of 94 meters per second. That's how fast it's traveling when it hits the ground. Okay, so we've seen that the same type of limit arises when we find the slope of a tangent line or the velocity of an object. And both of those limits have this standard form of the limit as h approaches 0 of f of a plus h minus f of a all over h. And in fact, this will arise anytime you calculate a rate of change in any of the sciences or engineering. So it's a very important formula. Things like marginal cost and economics, all sorts of applications. So it's very important that you understand how this works. Okay, here's the formal definition of the derivative of a function at a particular number. And we tend to like to use this notation the most for the derivative. F, we call that f prime. F prime at a, that's the derivative of the function at a point a, is equal to this. And then of course, if we go back and kind of do the substitution back to our original stuff, we can see that it also equals this equation. They're the exact same thing. There's really no reason why you would need to use one over the other. I would recommend using definition 4 more than definition 5, just because it's going to lead you towards the derivative of a function at x instead of at a lot easier. Here's another simple example. We have a simple simple function of x squared minus 8x plus 9. We want to find the derivative of the function at the number a. So that just means using that first limit formula that we had, f of a plus h minus f of a all over h, right? That means you now have to take a plus h and plug it into the function. That's why you have a plus h squared minus 8 times quantity a plus h plus 9. That whole thing is just the function evaluated a plus h. Then you got to go back and evaluate the function at a. Then you got to, FOIL out, distribute your minus 8, combine like terms, combine the stuff from the first one to the stuff to the second one, cancel out stuff, and all of a sudden you're left with just this. Okay, so make sure this makes sense, right? Follow all this, do it yourself. Don't just write it down. Do it yourself. Make sure you get the same response, because at this point, we're still just doing a bunch of algebra. Okay, and then you get this. Once again, if you plug in 0, you still get 0 over 0, which is no good. So you know there's got to still be some reduction left. And of course, the top is divisible by h. You divide out that h. You're left with 2a plus h minus 8. You can now let h go to 0, and the h, of course, just disappears, right? And then you're left with 2a minus 8. That is the equation of the slope at a point A. Right? So we're now finding the equation of the slope of the tangent line at just a generic point A instead of at a specific point A. If you wanted to find it for a specific point, you would have been better off just plugging in formula 5, because then you could just do f of x minus f of, let's say you wanted to find it at the point 3. Then f of 3 is much easier, right? You just use the original function, you do f of 3, you've got x minus 3, it's a lot easier to do the math, and you would actually get 2 times 3 is 6, 6 minus 8, you'd get an answer of -2 for your slope, right? So if you only have to do it for one number, it's easier to use that formula. But if you're going to have to find the equation of the slope of the tangent line at multiple places, multiple a's. You're better off doing this. Now you have this, and you don't have to do the limit ever again. You can now just plug in all the different a values to get all the different slopes. Okay, earlier we defined the tangent line at the curve, at the point A, f of a, just to be the line that passes through that point P and has that slope m given by equation that we saw earlier, equation 1 or 2. Since by definition 4 this is the same as the derivative, we can now say the following, that the tangent line to the function at some point is the line through that point whose slope is just equal to the derivative of the function at that point. So all we're doing is we're now relating those two ideas together, that the derivative at a point is the same thing as the slope of the tangent line at that point. And then this last thing here, we're just using the point slope form of a line, and we're plugging in the fact that the y1 is just the function evaluated at a, the x1 is just a, and the slope now is just the derivative at a. Okay, don't be confused by all that gobbledygook. It's just the same thing you already knew, that the slope of a tangent line is the same thing as the derivative of the function at that point. Okay, rates of change. We've already seen how rates of change are related to slopes, and they're thus related to tangent lines. Suppose y is a quantity that depends on another quantity x. So y is a function of x as we're normally used to. Y equals f of x. We know that if x changes from x1 to x2, then the change in x, which is sometimes also called the increment of x, is written as just delta x. The delta always means change. So that's change in x just equals x2 minus x1. It's how much x has changed. And then of course the corresponding change in y is called delta y, right? It's just going to be f of x2 minus f of x1. So now we can do the difference quotient of those two changes, right? Change in y over change in x. And this is called the average rate of change of y with respect to x. Again, nothing new. You've already seen this. You know this. This is just the slope of the line, right? It's change in y over change in x. We're just kind of formalizing the language. So therefore, by analogy with velocity, we can consider the average rate of change over smaller and smaller intervals by letting x2 and x1 get closer and closer. You can either let x2 approach x1 or x1 approach x2. It doesn't matter. It's the same idea, because in either case, delta x just gets closer and closer to 0. Therefore, if we take the limit as delta x goes to 0 of this change in y over change in x, we're getting the limit as x2 goes to x1, or in the other direction, right, of the f of x minus the other f of x over the x minus the x. And we can see that that is another way of describing the instantaneous rate of change, right? The average rate of change is when you don't take the limit, and then the instantaneous rate of change is when you just take the limit and let that delta x go to 0. So therefore, we now know that the derivative f prime of a is the instantaneous rate of change of the function with respect to x when x equals a, i.e., we know that the derivative gives us the instantaneous rate of change of the function at that point. This just means that when the derivative is really large, right, a large positive number, then we have a very steep curve, as we can see at point P. But when we have a derivative that's very small, close to 0, we get a shallow curve. And in fact, you can probably already start to figure out that if you have a curve with hills and valleys in it, and then you start doing tangent lines, well, this maximum value here is going to have a tangent line that's horizontal with a slope of 0, and this minimum is also going to have a tangent line with a slope of 0. So taking derivatives, setting them equal to 0, and solving becomes very important, because now that tells us what values of x are relative mins and maxes of our function. And that's what we're just talking about on this slide, that when the derivative is small, we get the curve is relatively flat. Okay, one last example. We can look at one that deals with kind of an economics slant. Let's say the cost of producing X yards of fabric is a simple function, right? Cost is some function of X dollars. We want to know what's the meaning of the derivative, what are the units. In practical terms, what does it mean to say that f prime of 1,000 equals 9? And what do you think is greater, f prime of 50 or f prime of 500 or f prime of 5,000? Okay, the derivative f prime of x is the instantaneous rate of change of our function. So it's the instantaneous rate of change of this cost function with respect to x. That means it's the rate of change of the production cost with respect to the number of yards produced. As you produce more and more yards of fabric, this is how fast your cost is now going up, or going down, depending on what's happening. Most likely it goes up, right, as you produce more things. The units of f prime are the same as the units for the different quotient, change in x over change in c over change in x. And since change in c is measured in dollars, right, how much your monetary cost is going up, and then change in x is measured in yards, we're going from 5 yards to 5.2 yards, etc., etc. It would make sense that the units for your derivative are going to be dollars per yard, right? We always say per when we divide by something, so dollars per yard. Okay, so therefore, the statement that f prime of 1,000 equals 9 means that when you're at x equals 1,000, so basically when you're producing 1,000 yards of fabric, the rate at which your production cost is increasing is $9 per yard. So as you change from 999 yards up to the 1,000th yard, or from the 1,000th yard up to the 1,001st yard, right, thereabouts, because we're pretending like we can't do a point of a yard. But basically, when you're changing from 1,000 plus or minus 1, it looks like your cost is changing by about $9. The rate at which the production cost is increasing per yard, right, as we've seen, because it told us that it told us f prime of 1,000 was equal to 9, a positive number, right? So it's an increase. So if that's the case, then it's most likely lower when x equals 500 than when x equals 50. That means the cost of making the 500th yard is less than the cost of making the 50th yard because of economies of scale. And that makes sense. Anybody who's taken some econ knows that if you have some set costs, some fixed costs, and then as you produce more and more things, you have a variable cost. But as you produce more and more things, those fixed costs get spread out over more and more things, right? So the cost per unit tends to go down. Lastly, the idea that as production expands, the resulting large-scale operation might become inefficient, there might be overtime costs, things like that, then you could actually have costs start to rise again. So it could be true that the derivative at 5,000 is actually higher than the derivative at 500. Obviously, these are all guesses. We don't know. We don't have the actual function, but we're just trying to relate it back to kind of a real-world example. And that is the basics of everything you need to know when you're dealing with derivatives and rates of change.